Hi, I'm Trevor Pisote. I'm a grad student at the UC Santa Cruz Genomics Institute, and I'll be introducing genomic workflows to you all today. I'll start by motivating why workflows are important, go through the architecture of a workflow, and finish by walking you through the process of building and running your first workflow. The HPRC has developed a collection of workflows used to generate and evaluate the assemblies which are building the human pangenome. The code for these workflows is available on GitHub and on a workflow hosting platform called DocStore. So, why would you want to use a workflow for genomic analysis? Well, the first reason is for consistency and reproducibility. We don't want the results of the same analysis to differ. They were performed by different groups or different users. Using a specific container with specific tool versions and a specific pipeline of steps will ensure consistency across runs. The second reason is that it's much easier. It's a pain to have to manually run data pipelines, and it's really untenable to do it on the huge data sets that are available today. Lastly, it creates a resource that the community can use, and it centralizes this knowledge in one repository where experts can all work on it together. This helps keep the industry's knowledge up to date and available for all. So, what is a workflow? At a high level, it can be broken into three parts. First is a container. A container is a lightweight virtual machine compiled with specific tools and specific versions. This provides the consistency across groups running a workflow. For all the work done by the HPRC in AnVIL, we use a container technology called Docker. Next is the workflow descriptor file. This is where we describe the actual steps that are taken, what order they're taken in, and what data is needed as input and output. It's possible to specify the specific hardware resources that your workflow needs on a task-by-task basis. There are also a few workflow languages, all which have a pretty similar structure. Today I'll be introducing Workflow Description Language, or WDL. Last, we need to know what data to run a workflow on. How you specify the data depends on what platform you're using to run the workflow. If you're running locally, this will probably be a JSON file. If you're running on AnVIL, you'll either enter it into the GUI or read it from a data table. Workflow description language is the specification for workflows that AnVIL has adopted. It's human readable and straightforward to write. The workflow is broken up into single pieces of work called tasks. Each task has inputs, outputs, and the actual work itself can be described in Bash or Python or R. Similar to a task, a workflow also has inputs and outputs. In a workflow definition, tasks are tied together with support for complex chaining and parallelization. Today, I'm going to walk you through the creation of a workflow we use in the HPRC to evaluate the accuracy of a diploid assembly. It uses YAC, yet another K-mer analyzer, developed by Heng Li's group. This workflow generates K-mer databases for a sample and its two parents, and then uses these databases to evaluate the sequence accuracy of both assembled haplotypes, as well as the switch error rates between them. Before we start, I'd just like to note that for demonstrative purposes, the workflow I'm presenting today has been slightly modified from the version used in production, which you can see on the HPRC GitHub. First, we start by building a Docker container. Containers extend from an existing container. In this case, we have a base container for the Human Pangenome project with tools that are consistently needed across tasks, such as Python or SAM tools. Often people will extend just from the base Ubuntu image. It's possible to specify metadata, in this case, the maintainer. The real work starts when we indicate a directory to work in. And then we identify a series of commands that we want to run in order to install the application and its prerequisites. In this case, we check out a specific commit from the YAC repo, so we know exactly what code we're getting, and compile the tool. Last, we add this directory to our path so that the workflow's tasks can use it without having to know the specific location of the tool in the container. Next is building a task. We start with a task keyword, an identifier, and curly brackets. Then we define our inputs. WDL supports a variety of data types. In this case, we need a set of reads, a set of files. This is our read data, an identifier for the task, and a parameter, the bloom size, which is used by YAC. When the task is run, these files will be localized and a path to its location in the container will be provided. A default value is provided, you see here, for one of the parameters. This is one way to specify that an input is not required, but there are other ways to show that an input is optional. Now we're going to specify the command we're going to run. In this case, we have a simple single line command in Bash, but the command definition can be as long or as complicated as the user needs. You can see in this command, we have variables that reference the inputs directly. And we also have ways to interact with an array of inputs using the separator or sep keyword. Next, we identify outputs. This YAC command will produce an output file, which we know the name of, so we can reference it directly using a variable defined in the inputs. There are also ways of specifying output that can read text from a file or select multiple files using the glob command. Last, we're going to specify our runtime attributes. The most important is the Docker image that the task should be run on. Then we have a set of resource specifications which tell the provisioning engine, if the engine supports it, what type of instance to run this task on, enabling fine-grained resource management. It's possible to specify how many gigs of memory are needed, what the core count should be, and the type and amount of storage needed. We can also specify whether this is allowed to run on a preemptible instance for improved savings. AnVIL also supports specifications for GPUs, including the type, count, and driver version, as well as which availability zone to run in. These values can be hard-coded, such as whether this task can be preempted in this example, or specified through input variables such as the Docker image identifier, memory thread count, etc. In some of our workflows, we'll determine the size of an output file from one task and then use that to specify how much disk we need in a downstream task. Okay, now we're done with our tasks. Let's tie them together with a workflow. The specification for a workflow is very similar to a task. We use the keyword workflow, given an identifier, and wrap it in curly brackets. Then we're going to specify inputs. In this case, we need our 2 assemblies, 3 sets of short reads for the sample, its mother, and its father. Next, we tell the workflow which task to call. Here we call the task we just built YAC count on each of the data sets, giving a different identifier to each run. Each task has the required input file specified. Then we can take the output of each of these tasks and pass it on to a second task. I haven't shown you this one, but it's the one that generates the statistics we care about and is available on GitHub for you all to review. The engine can determine that the 3 YAC count tasks need to be run first, but they can be run in parallel. And then after they've successfully completed, we can run the assembly stats task. Note that not all of the potential inputs for the tasks are specified. We'll get into this later. Last, we identify our outputs. In this case, we want to preserve the maternal and paternal K-mer files and the 2 outputs from our assembly stats task. The first, a tarball containing all the information generated, which a scientist may care to poke through on a case-by-case basis, and a summary file, which can be read easily by AnVIL on a Jupyter notebook to collate results across all the assemblies. Now, our workflow is done. All that's left is to test and run our workflow locally. It's also possible to test on AnVIL as well, but I personally prefer to do this on my laptop first. There are multiple different softwares that will allow you to run workflows, but I use Cromwell. It's an application developed by the Broad Institute. This tool comes with 2 jar files. The first is WOM tool, and you can use this to validate your workflow as well as generate an input file. Here's an example of the input JSON file for this workflow. you can see that there are inputs required by the top-level workflow, as well as the optional inputs for each task which weren't filled out during our workflow definition. All these values can be specified here. In this example, I'm going to give paths to local files for our file inputs, and I'm going to use a different Docker image than the default. All the other parameters which I've not specified will be populated with the default. Then you can use the Cromwell jar to run your workflow. Here's an example command for how to run it, and there's full documentation on the Cromwell GitHub page. Now you should understand all the parts of a workflow and have the tools necessary to start writing your own. Thank you.